Good morning. Today we're going to talk about a new balanced search structure, so a data structure that maintains a dynamic set subject to insertion, deletion, and search, called skip lists. So I'll call this a dynamic search structure because it's a data structure, it supports search, and it's dynamic, meaning insert and delete. So what other dynamic search structures do we know, just for sake of comparison, and to wake everyone up? Shout them out. Good, efficient, I should say. Also good. Logarithmic time per operation. So this is a really easy question to get us off the ground. Seen them all in the last week, so it shouldn't be so hard. Treep, good. On the problem set we saw treeps. That's in some sense the simplest dynamic search structure you can get from first principles, because all we needed was the bound on a randomly constructed binary search tree, and then treeps did well. So that was sort of the first one you saw, depending on when you did your problem set. What else? Charles. Red-black tree is a good answer. So that was exactly 1 week ago. Hope you still remember them. They have guaranteed log n performance. So this was a expected bound. This was a worst case order log n per operation. Insert, delete, and search. And there was one more. For those who went to recitation on Friday. It's rather in B trees, good. And by B trees, I also include 2, 3 trees, 2, 3, 4 trees, and all those guys. So if B is a constant, or if you implement your B tree nodes a little bit cleverly, then these have guaranteed order log n performance. So worst case order log n. So you should know this. These are all balanced search structures. They're dynamic. They support insertions and deletions. They support searches, finding a given key. And if you don't find the key, you find its predecessor and successor pretty easily in all of these structures. If you want to augment some data structure, you should think about which one of these is easiest to augment, as in Monday's lecture. So the question I want to pose to you is, suppose I gave you all a laptop right now, which would be great. But then I asked you, in order to keep this laptop, you have to implement one of these data structures, let's say within this class hour. Do you think you could do it? How many people think you could do it? One, a couple people, a few people, okay. All front row people, good. I could probably do it. My preference would be B trees. They're sort of the simplest in my mind. This is without using a textbook. This would be a closed book exam. I don't have enough laptops to do it, unfortunately. So B trees are pretty reasonable. Deletion, you have to remember this stealing from the sibling and whatnot. So deletions are a bit tricky. Red-black trees, I can never remember. I'd have to look it up or rederive the 3 cases. Treeps are a bit fancy, so that would be take a little while to remember exactly how those work. You'd have to solve your problem set again if you don't have it memorized. Skip lists, on the other hand, are a data structure you will never forget, and something you can implement within an hour, no problem. I've made this claim a couple times before, and I always felt bad because I'd never actually done it. So this morning, I implemented skip lists. And it took me 10 minutes to implement a linked list and 30 minutes to implement skip lists. And another 30 minutes debugging, but there you go. It can be done. Skip lists are really simple. And at no point writing the code did I have to think. Whereas every other structure, I would have to think. There was one moment when I thought, how do I flip a coin? Okay, that was the entire amount of thinking. So skip lists are a randomized structure. Let's add in another adjective here. And let's also add in simple. Okay, really cluttered. So we have a simple, efficient, dynamic, randomized search structure. All those things together. So it's sort of like treeps in that the bound is only a randomized bound. But today we're going to see a much stronger bound than an expectation bound. So in particular, skip lists will run in order log n expected time. So the running time for each operation will be order log n in expectation. But we're going to prove a much stronger result, that they're order log n with high probability. So this is a very strong claim. And it means that the running time of each operation, the running time of every operation is order log n almost always, in a certain sense. Why don't I foreshadow that? So it's something like the probability that it's order log n is at least 1 minus 1 over some polynomial on n. And you get to set the polynomial however large you like. So what this basically means is that almost all the time, you take your skip list, you do a polynomial number of operations on it, because presumably you're running a polynomial time algorithm that's using this data structure. You do polynomial numbers of inserts, deletes, searches. Every single one of them will take order log n time, almost guaranteed. So this is a really strong bound on the tail of the distribution. The mean is order log n. That's not so exciting. But in fact, almost all of the weight of this probability distribution is right around log n. Just tiny little epsilons, very, very tiny probabilities you could be bigger than log n. So that's where we're going. This is a data structure by Puig in 1989. So this is the most recent. Actually, no, sorry. Treeps are more recent. They were like 93 or so. But a fairly recent data structure for just insert, delete, search. And it's very simple. You can derive it if you don't know anything about data structures. Well, almost nothing. Now, analyzing that the performance is log n, that, of course, takes our sophistication. But the data structure itself is very simple. We're going to start from scratch. Suppose you don't know what a red-black tree is. You don't know what a B tree is. Suppose you don't even know what a tree is. What is the simplest data structure for storing a bunch of items? For storing a dynamic set? A list. Good. A linked list. Now, I'm going to suppose that it's a sorted linked list, so I'm going to be a little bit fancier there. So if you have a linked list of items, here it is. Maybe we'll make it doubly linked just for kicks. How long does it take to search in a sorted linked list? Log n is one answer. N is the other answer. Which one's right? N is the right answer. So even though it's sorted, we can't do binary search because we don't have random access into a linked list. So I suppose that I'm only given a pointer to the head. Otherwise, I'm assuming that it's an array. If it's a sorted array, you can search in log n. Sorted linked list, you still got to scan through the darn thing. So theta n worst case search. Not so good. But if we just try to improve it a little bit, we will discover skip lists automatically. So this is our starting point. Sorted linked list, theta n time. And I'm not going to think too much about insertions and deletions for the moment. Let's just get search better, and then we'll worry about updates. Updates are where randomization will come in. Search, pretty easy idea. So how could we make a linked list better? Suppose all we know about are linked lists. What could I do to make it faster? This is where you need a little bit of innovation, some creativity. More links, that's a good idea. So I could try maybe, I don't know, add pointers to go a couple steps ahead. You know, if I had log n pointers, I could do all powers of 2 ahead. That's a pretty good search structure, and some people use that in various, like some peer-to-peer networks use that idea. But that's a little too fancy for me, yeah.
If you give each node 2 pointers, the 2 nodes that you might want if you're doing a binary search.
Ah, good. You could try to build a tree on this linear structure. That's essentially where we're going. So you could try to put pointers to maybe like the middle of the list from the root. So you search between either here. You point to the median, so you can compare against the median and know whether you should go in the first half or the second half. That's definitely on the right track. Also a bit too sophisticated. Another list, yes. Yes, good. So we're going to use two lists. That's sort of the next simplest thing you could do. Okay, and as you suggested, we could maybe have pointers between them. So maybe we have some elements down here, some of the elements up here. We want to have pointers between the lists. Okay, it gets a little bit crazy in how exactly you might do that, but somehow this feels good. So this is one linked list, L1. This is another linked list, L2. And to give you some inspiration, I want to give you, so let's play a game. Game is, what is this sequence? So, sequence is 14. If you know the answer, shout it out. Anyone yet? Okay, it's tricky. Bit of a small class, so I hope someone knows the answer. How many TAs know the answer? Just a couple. If you're looking at the slides, probably you know the answer. That's cheating. Okay, I'll give you a hint. It is not a mathematical sequence. This is a real-life sequence. Yeah.
Are they able to stop on one of the subways?
Yeah. In what city? New York. Yeah. This is the 7th Avenue line in New York City. It's my favorite subway line in New York. But what's a cool feature of the New York City subway? It's a skip list. Good answer. Indeed it is. If you want to experience, see, skip lists are so practical. They've been implemented in the subway system. How cool is that? Okay. Boston subway is pretty cool because it's the oldest subway definitely in the United States, maybe in the world. New York is close, and it has other nice features like it's open 24 hours. That's a definite plus. But it also has this feature of express lines. So it's a bit of an abstraction, but the 7th Avenue line has essentially two kinds of cars. These are street numbers, by the way. This is, Penn Station, Times Square, and so on. Okay, so there are essentially two lines. There's the express line, which goes 14 to 34 to 42 to 72 to 96. And then there's the local line, which stops at every stop. And they accomplish this with 4 sets of tracks. So the express lines have their own dedicated track. If you want to go to stop 59 from, let's say, Penn Station, well, let's say from Lower West Side, you get on the express line, you jump to 42 pretty quickly, and then you switch over to the local line and go on to 59 or wherever I said I was going. Okay, so this is express and local lines, and we can represent that with a couple of lists. We have one list, we have one list on the bottom, so leave some space up here. This is the local line, L2, 34, 42, 50, 59, 66, 72, 79, and so on. And then we have the express line on top, which only stops at 14, 34, 42, 72, and so on. Okay, I'm not going to redraw the whole list. You get the idea. And so what we're going to do is put links between the local and express lines, wherever they happen to meet. And that's our two-linked list structure. So that's what I actually meant when I was trying to draw some picture. Now this has a property that in one list, the bottom list, every element occurs. In the top list just copies some of those elements. And we're going to preserve that property. So L2 stores all the elements. And L1 stores some subset. And it's still open which ones we should store. That's the one thing we need to think about. But our inspiration is from the New York subway system. Okay, there. That's the idea. Of course, we're also going to use more than two lists, but okay. We also have links, let's say links between equal keys. In L1 and L2. Good. So just for the sake of completeness, and because we'll need this later, let's talk about searches before we worry about how these lists are actually constructed. Of course, I wanted that board. So if you want to search for an element, X, what do? Well, this is the taking the subway algorithm. Okay, and suppose you always start in the upper left corner of the subway system. So you're always in the lower west side, 14th Street, and, or I don't know exactly where that is, but more or less, somewhere down the bottom of Manhattan. And you want to go to a particular station like 59, well, you stay on the express line as long as you can, because it happens that we started on the express line. And then you go down, and then you take the local line the rest of the way. That's clearly the right thing to do if you always start in the top left corner. So I'm going to write that down as some kind of algorithm, because we'll be generalizing it. It's pretty obvious at this point. Will remain obvious, but... So I want to walk right in the top list until that would go too far. So you imagine giving someone directions on the subway system they've never been on. So you say, okay, you start at 14th, take the express line, and when you get to 72nd, you've gone too far. Go back one, then go down to the local line. So really annoying directions. But this is what an algorithm has to do, because it's never taken the subway before. So it's gonna check. So let's do it here. So suppose I'm aiming for 59. So I start at 14. Say, okay, first thing I do is go to 34. Then from there I go to 42. Still good because 59 is bigger than 42. I go right again. I say, oops, 72 is too big. That was too far. So I go back to where I just was, then I go down, and then I keep going right until I find the element that I want or discover that it's not in the bottom list, because bottom list has everyone. So that's the algorithm. Stop when going right would go too far, and you discover that with a comparison. Then you walk down to L2, and then you walk right in L2. Until you find X, or you find something greater than X, in which case X is definitely not in your list, and you found the predecessor and successor, which may be your goal. If you didn't find where X was, you should find where it would go if it were there, because then maybe you could insert there. We're going to use this algorithm in insertion.